Professor Dave and Chegg here. We just learned about SP3 hybrid orbitals and the tetrahedral geometry that methane adopts because of these orbitals. Let's now move on to SP2 orbitals and the types of molecules that utilize them.
Previously, we saw that the carbon in methane is sp3 hybridized because it is surrounded by 4 electron domains, the 4 hydrogen atoms. When an atom is surrounded by 3 electron domains, it will be sp2 hybridized. This could be something like Bf3, where boron has only 3 valence electrons and thus can participate in only 3 covalent bonds. In this situation, we will get 120-degree bond angles and trigonal planar geometry. But things get a bit more complicated when looking at molecules with multiple carbon atoms that participate in either double or triple bonds. As we already know, covalent bonds occur due to orbital overlap, but the type of bond that forms will depend on the types of orbitals and the type of overlap that is occurring. First, let's distinguish between sigma bonds and pi bonds. Looking at C2H6, we see 2 sp3 hybridized carbons. All the bonds occur due to direct overlap of orbitals, either with 2 hybrid orbitals between the 2 carbons, or with 1 hybrid orbital and the 1s orbital from a hydrogen atom. These are all sigma bonds because they involve direct orbital overlap along the internuclear axis. As long as these orbitals are overlapping in this manner, the bond is present, which means sigma bonds can rotate freely. Orbitals can spin, and the bond will not break. Now let's look at ethylene, or C2H4, which has a double bond between the carbons. Now the carbons are each surrounded by only 3 electron domains and are thus sp2 hybridized, exhibiting trigonal planar geometry. And because each carbon only needs 2 of its 2p orbitals to generate the hybrid orbitals, each has 1 unhybridized p orbital left over. Lateral or side-by-side overlap of these unhybridized p orbitals will result in what is called a pi bond. So between these 2 carbons there is 1 sigma bond due to direct overlap of sp2 hybrid orbitals, and there is 1 pi bond due to lateral overlap of these unhybridized p orbitals, meaning they point in a direction that is perpendicular to the internuclear axis, and then overlap in side-by-side fashion, while the 4 hydrogen atoms form sigma bonds with the 4 remaining sp2 hybrid orbitals. Unlike sigma bonds, pi bonds restrict rotation, because if we were to twist this molecule, the p orbitals would no longer overlap and the bond would break. So, rotation is restricted around pi bonds and therefore double bonds, because any double bond consists of 1 sigma bond and 1 pi bond. We should note that carbon-carbon double bonds are both shorter and stronger than single bonds due to the additional orbital overlap provided by the pi bond, although not precisely twice as strong since the lateral overlap of the pi bond is not as significant as the direct overlap of the sigma bond.
With sp2 orbitals and the geometry of ethylene now understood, let's move forward and look at one more type of hybrid orbitals. Professor Dave for Chegg. See you next time.